Okay, in this video I am going to continue my tutorials on thermodynamics and statistical mechanics. So this is tutorial number 13. The previous tutorial to this I discussed the binomial theorem, and while the binomial theorem isn't important here, I would recommend that you check out my tutorial videos on power series representations of functions. I did quite a few videos on power series. So let's begin. So what is a Taylor series? A Taylor series, the bottom line up front, is this particular expansion here, where we assume that we can expand our function f of x by adding up lots of different smaller terms. So I'm hoping that you understand what I mean by a power series representation. If not, look up my other videos. But just a very quick recap. Let's say that we have our function f of x, but it's sometimes difficult to calculate f of x directly. So instead of calculating f of x, we calculate, at these smaller pieces. So let's say piece 1, this is piece 1, piece 2, piece 3, and so on. And once we add up all the different pieces together, we can get the exact answer for what f of x actually is, but we have to add up an infinite number of terms, which of course is impossible. So usually what we do is we truncate at some point. We'll say, let's say power or piece 3 or whatever it is, or term 3, and as a result we're going to get an approximation of our function. So that's generally how these power series representations work. So what we'll do is we'll show that by doing that we can get the Taylor series. So the Taylor series is basically just a power series expansion of a function. So what do we mean when we say it's a power series expansion? Let's say there's our function f of x. Well, we add up the terms in a power series like this. So we assume, and it's quite a leap of faith, quite a jump, but we assume that we can expand our function as follows, where we have these coefficients. C sub n is the nth coefficient, multiplied by x minus a to the n. And well, if we do that, we're going to get c0 plus c sub 1 times x minus a plus c sub 2 times x minus a to be squared, and so off to infinity. Just to note, by the way, that's actually c sub 0 times x minus a to the 0. So anything to the power of 0 is 1. We usually just don't bother writing that term. So that's our starting point. We assume that we can expand our function as a power series. Now, when is that a valid assumption? I'm not going to discuss. But we also assume two other things. We assume that f of x is continuous, and we assume that each of the derivatives of x are continuous. Alright, and can be found. So what does continuous mean? Well, if you draw it, let's say you're drawing in 2 dimensions on our Cartesian plane, well then this is a continuous function because I can draw it with one pen stroke, or there are no breaks. However, this would be a discontinuous function. That's a discontinuous function. And why are discontinuities awful? Well, the reason is because they have no derivatives, or they have an infinite number of derivatives. Remember, a derivative can be thought of as a tangent line at a particular point. But let's say this point here, or this point here, let's say this is B and this is A. There are two discontinuities. Well, that's a tangent line, so is that, and you get the point. So that there are an infinite number of derivatives. In other words, we can't get the derivative. And for this particular Taylor series, because as you'll see, we'll be getting derivatives, they also must be continuous. So, because we're going to be using them, and we can't use a derivative which is discontinuous. Alright, so that's our starting point. Now, I'm going to dispense, I suppose, with mathematics, or the rigorous mathematics, by saying let's just assume that in general we can expand something as a power series and ignore the discontinuities and all that sort of thing, because unless you're dealing with theoretical physics or you're a hardcore mathematician, those things are unimportant. They don't usually pop up. So let's start from there. So we have our power series. So let's look at expanding our power series at some point, x is equal to a. So we want to center our function around x is equal to a. Well, what does that mean? Well, let's think about the function x squared drawn on our y is equal to x squared drawn on our Cartesian plane. Right, well, it looks like this. So there's, well, that's actually not correct because I've not centered it at 0. This function is centered at 0, but this function here is not. It's centered at x is equal to a, where this point here is equal to a. Now, the function y is equal to x squared is this one. That's centered at the origin, or centered at a is equal to 0. But if we shift or move our function, then we now center it at a new point. Now, how do you visualize this with a more complicated expression? I'm not going to go into. That's not the point. The point is here is that you should be able to accept that you're able to move your function along the plane, and yet it is the same function. It's just centered someplace else. And once you can accept that point, we can now move on. So, what if we've centered our function at x is equal to a? So, well, what's f of x is equal to a? So, plug it into that expression there, and I'm telling you, you're going to get you'll get the first coefficient, or c sub 0. So this is n is equal to 1, or n is equal to 0 in fact. Alright, now what if we look at the derivative of this? And I'll let you do the groundwork, I'll let you do the derivatives if you like, they're very straightforward. We're just going to get c sub 1. And if we look at the third derivative, centered at x is equal to a, you're going to get twice c sub 2. And finally, if you get the fourth derivative, 1, 2, 3, 4, of x is equal to a, will we get the, actually, no, I won't. Sorry, this is the first derivative, that's the second derivative, and this is the third derivative. So we center the third derivative at x is equal to a. What we're going to get is 6 times c sub 3. Or, what we're actually getting is 2 times 3 times c sub 3. And you can imagine continuing this on to the nth derivative. What's the pattern? The pattern is a factorial. Or, we could say, so let's look at these three. Don't mind the first one. So let's just look at the n is equal to 1, 2, and 3. The point is here is that, well, the derivative is the coefficient multiplied by, in this case, 1 factorial, 2 factorial, 3 factorial, or n factorial, because here n is equal to 1, n is equal to 2, n is equal to 3. So there is some n factorial term involved. So can we rearrange these formulas here? If we do, we'll get c sub 3 is equal to the third derivative at a divided by 3 factorial. Okay? Or we could say c sub n is equal to the nth derivative centered at x is equal to a divided by n factorial. Okay? And this particular formula allows us to calculate all the different various coefficients in our power series. So go back to our power series expansion of our function f of x. We now know what each of these coefficients is. We know that c sub n now is equal to the nth derivative of our function centered at x is equal to a divided by n factorial. Very simple. So what I'm going to do now is plug that in and rewrite the formula in terms of that. And that is our Taylor series expansion. So f of x is equal to the infinite power series of the nth derivative centered at x is equal to a multiplied by x minus a to the n divided by n factorial. So let's write out some of those terms. We're going to get f of a, we'll say, I'm going to write it this way, f of x is equal to a. That's where we're going to center it. I'm going to write it in the following way. Okay, where x minus a to the 0 is 1, and that should be 0 factorial, which is also 1. Plus so on, you get the picture. And that's it. So, you know, that's pretty straightforward. You might say, well, okay, I understand how that was made. How do I use it? Well, look at tutorial video number 13, 14. Sorry, 14 and 15, and you'll see, because I'll do it using examples. Now, So this is the Taylor series. Now a, of course, can take up any value. You can center your function anywhere you like, and I'm going to tell you that if you center your series at a is equal to 0, we call it the MacLaurin series. So a is equal to 0, Taylor becomes MacLaurin. Is it E or A-N? M-A-C-L-A-U or I-N, I think, actually. I'm open to correction on that. So the point here really is that the Taylor expansion is the more general expansion of a function who is continuous at all points, its derivatives are continuous, and the derivatives can be found. And it can be expanded as a power series. But it's very useful, especially in physics, and we'll see that in a moment. So thanks for watching. Please pass it on to your friends. Subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.